Have I got this on? Yes. I want to thank the organizers for inviting me to this important conference. In 1962, there were several events for mathematics. One was very small, and that's what I'll be talking about. And the other was very large, and that's why we're all here. So let me go on to describe the problem I want to talk about. So here's the background. We start with a Riemannian manifold, say connected, simply connected, and homogeneous. So the group of isometries is transitive. And we read it as a quotient where G is the isometry group, and K is a stability subgroup, isotropy subgroup. Now I want to look at a Riemannian covering. That is a covering space where the local maps for the covering are local isometries. Now the problem is, so this situation, of course, the base space of the covering is locally homogeneous, but the question is, when is it globally homogeneous? In other words, when is the group of covering transformations, which we take as a discrete subgroup of the isometry group, where every element has no fixed point, unless, of course, it's the identity. So the question now is, when is the quotient globally homogeneous? Well, the first step here is very nice, I think, description. So I take 2 points on M, and I look to see what happens when I move them under a covering transformation. So I look at the displacement. Suppose this is X. This is Y. So I look to see how much they're moved. And the interesting thing here is that if the base space is globally homogeneous, then well, I use the other side. Okay. Oh, I see. If the base space is globally homogeneous, then this displacement function is constant, because I can write y as g of x, where g centralizes gamma. The point being that I take, if it's globally homogeneous, I can take the isometry group of the quotient and lift that. Then it normalizes the group gamma. So its identity component centralizes the group gamma. And that's still transitive. So I can take an element, I can go from one element to another by something that centralizes gamma. And once I have that, the displacement of gamma x, that's going to be the same as the displacement of g gamma x gx. And that'll be the displacement of gamma gx, gx, which is the same as the displacement of gamma y, y. So the displacement then, the amount that each point has moved, is the constant. So this is a very pretty geometric situation to say that every point gets moved the same distance. Now I'm going to describe some examples of this. And there are so many examples that one thinks that the converse must be true. That if you have a Riemannian covering, and from a simply connected Riemannian homogeneous space down to locally homogeneous, of course, and if every deck transformation, every covering transformation is constant displacement, then you want to see whether, and you expect that the quotient is homogeneous. That's the homogeneity conjecture. Now, when I mentioned some events of 1962, that's the small event. But that's what I want to talk about now. So the first step, that's what I talked about, the isometry being constant displacement. And let's look at a trivial example where we start out with Rn, the Euclidean space with the usual Euclidean metric. So what would it mean for every point isometry to have constant displacement on Rn? Well, one thing it would say is that you take a line, you look at the image of that line. Now, the two can't cross because then it would go apart. And the two, in fact, can't be twisted because then it would go apart. So they must be parallel. The line must be sent to a parallel line. Okay. So in 7th or 8th grade, we learned that if two lines don't diverge, of course it's not phrased that way in 7th grade, but anyway, if every line is sent to a parallel line, then the isometry must be an ordinary Euclidean translation. So in this case, gamma consists of ordinary Euclidean translations. So the quotient's the product of a torus and another Euclidean space, and that is homogeneous. Okay, so it seems to work for Rn. Now let's look at a less trivial example. Let's suppose that M has sectional curvature less or equals 0. Actually, this will work for a Ricci curvature less or equals 0 or for no focal points, but let's just say for sectional curvature less or equals 0. Now, we can write, since M is connected, simply connected, and it's complete because it's homogeneous. With the de Rham decomposition, writes it as a product of a Euclidean space and some spaces with where the holonomic group, the group parallel translation around closed curves, is irreducible. And if you take an isometry of constant displacement, say, on such a product, each factor, it preserves each factor, and each factor is constant displacement. That's an easy thing to check. Okay, so now M has every sectional curvature less or equals 0, and we already know about the Euclidean factors, so let's just look at the irreducible part. Okay? So now we're looking at the universe Riemannian covering, and then I claim the following are equivalent. And this, of course, is assuming that the sectional curvature is less or equal to 0. First of all, that the quotient is homogeneous, also the isometry of constant displacement, or an isometry of bounded displacement, or just a pure translation along the Euclidean vector. Well, this is fairly straightforward. Let me quickly draw another picture. The idea is this, same idea as for Euclidean space. You take a geodesic, you look at the image. Now every point has an image, and because of the way I said with sectional curvature less or equal to 0, there's a unique piece of geodesic joining these. So in this way, you fill out, well again, these can't meet because if they did, they diverge apart. You wouldn't have bounded displacement. So just from bounded displacement, you fill out, you get a nice ribbon. And the ribbon has, we're assuming gamma is bounded displacement, for example, then the ribbon has finite width. Now, if you look at the structure equations, you see that this is going to be totally geodesic, curvature less or equal to 0, but it's going to be flat in between and totally geodesic. So there's something wrong unless you're in the Euclidean factor. So what's happening is every bounded displacement, oops, pressed the wrong button. Every bounded displacement, can I turn off the light? Yeah. Every bounded displacement isometry is just translation along the Euclidean factor. So again, this homogeneity theorem is okay. Now let's look at a non-trivial example. Let's look at the usual round sphere in dimension n-1 in Rn, and a finite group of fixed point free isometries. So the quotient is a so-called spherical space form, a compact manifold of constant positive curvature. Now let's suppose that it's homogeneous. So I'll take sort of thing I was doing before. I'll take the normalizer of gamma inside the isometry group of the sphere, which is the orthogonal group. And this identity component of that normalizer centralizes gamma. And also it's transitive on the sphere. Because transitive on the sphere, it certainly is irreducible on the Rn. So we have Schur's lemma, which tells us that that identity component is contained in the multiplicative group of a real division algebra, which of course we know very well is the reals, the complex numbers, are the quaternions. So now let's look at the cases. Gamma now is a multiplicative subgroup, is a subgroup of the multiplicative group of non-zero elements in that division algebra. So in the real case, it's contained in plus or minus the identity. In the complex case, it's contained in the cyclic group for rotation. Quaternion case, It's also the double covering of the isometry group of a classical symmetric solid. It's a binary dihedral group, tetrahedral group, octahedral group, or icosahedral group. And in any case, the point is that we know exactly what gamma has to be, and we know that it's centralizing, well, okay, so we know exactly the situation, and in this situation, the homogeneity conjecture is visible. It's clearly okay. Now let me look now. We can look in a slightly more general situation. Let's look at the case just where we have constant curvature, constant sectional curvature, say. So M is complete, constant sectional curvature, and say it's every element of gamma is an isometry of constant displacement, okay? So in this case, if the curvature is less than 0, we know already that gamma is trivial, so it's immediate that the quotient, which is not a quotient at all, is homogeneous. If k is 0, well, that's just the Euclidean space, so we know that, again, the quotient is homogeneous. And if k is positive, that gets a little tricky. One has to know something about spherical space forms and do some calculations, but it works out okay. You have to look at each element and see how they fit together, and look at the structure, a little bit about the structure of finite groups involved in spherical space forms, and still it's okay. So the homogeneity conjecture is correct in the case of constant sectional curvature. Okay, all this is from the 60s. Let me mention a few references. I should point out that Georges Vincent's paper was pretty much completed in the late 30s, but then he was in the Swiss Army during World War II and not thinking about mathematics. And then afterwards, he got together as a student of Heinz Hopf and completed what he did, which was they look at the case where gamma is metabillion and see which are the corresponding spherical space forms. Okay, so the next thing I want to talk about, the next situation, somewhat more general, is where M is, say, Riemannian symmetric space. And then again, I claim that M, the Riemannian quotient, is homogeneous if and only if every element of each of these transformations is constant displacement. So we have to figure out what are the isometries of constant displacement. Well, as I mentioned with using de Rhams' theorem, you can reduce to the case where M is either a Euclidean space or a so-called irreducible symmetric space. If so, then the first thing to look at would be if the irreducible symmetric space is non-compact type. We already know about that. It has sectional curvature less or equals 0. So we only have to worry about the case where the symmetric space is compact type. In other words, where M is compact and irreducible. And then there are two cases. It might be a compact, simply connected connected Lie group viewed with a Riemannian metric invariant under left and right translations. In other words, a negative multiple of the Killing form. Or it might be a situation where the isometry group is a simple classical group or a simple exceptional group. So how do you deal with these cases? So maybe at this point it's worth, I'll come back to these, how one deals with these cases. I'll come back to that in a few minutes. In the meantime, again, here are some references. The general result is published in the commentary in 1962. And then my student, then Hans Freudenthal came up with a different proof, which handled the case where gamma is contained in the identity component of the isometry group of M. And then my student Vilnius Osels came up with a third proof for the case, again for the case where gamma is contained in the identity component of the isometry group of M. Now, to look for the general case, one depends on a theorem of Élie-Cartan, which tells you what is the full group of isometries of a Riemannian compact, irreducible Riemannian symmetric space, G mod K. The full group of isometries is obtained by adjoining, well, of course, the symmetry. But in addition, the automorphisms of K, which extend to G. So with the symmetry, you've got a group which is either connected or two components, depending on whether the symmetry is inner or outer automorphism. And then you have to look at the automorphisms of G, of K, which extend to G, and those will add more components. So that has to be dealt with, and that is a good part. Whoops. That's a good part of this first paper. Well, incidentally, I should mention that this also works for Finsler symmetric spaces. So if you have a Finsler symmetric space, again, the quotient is Finsler homogeneous if and only if every element of the isometry group, of the deck transformation group, is constant displacement. And the way the argument goes is first you have to prove that it's Baerbold, and then you have to reduce to the irreducible case, which is not so obvious for Finsler. And then you have to deal with Minkowski and the non-compact types. And finally, for the compact ones, you have to reduce to the Riemannian situation. So when S.S. Chern was at Berkeley and was going to Nankai University, to Tianjin, 2 days before he left Berkeley, he said to me, he said, Joe, you should look at Burwald symmetric, Burwald symmetric spaces. So I knew what a symmetric space was, but I didn't know what Burwald meant. Eventually, I figured it out. I mean, I understood or studied. I get very roughly speaking, the structure equations for Riemannian manifold have 2 terms. For a Finsler manifold, they have 4 terms, and Burwald gets rid of one of those 4 terms, roughly speaking. Okay. So then Chern was on the mark, and oops. And it turned out to be correct for Finsler manifolds. Okay. Now, I'll go into the proofs later, but it's one thing to have the group gamma contained in the identity component of the isometry group, but you also have to worry about the other components. So in order to have much hope of this, you have to be able to either somehow eliminate the other components from the group gamma, or understand at least what is the entire isometry group. Now for Riemannian manifolds which are strictly positive curvature and so-called normal homogeneous metric, those are classified, it turns out. And for those, the full isometry group was figured out by Ravi Shankar. And he also proved that if you took the metric and moved it from normal to arbitrary, but keeping it positive curvature, at worst, the isometry group got smaller, so you still had an idea of what were the components. So that allowed one to deal with the case of positive curvature, at least more or less. So let me mention. So again, the first is first reduction was to a case where M is not a sphere, and you have the normal Riemannian metric and use the classification and calculation. And then you have a sort of a twister bundle because many manifolds might have a quotient where the fiber and the base are both manifolds, you know, like Riemannian symmetric spaces. Okay, so and then you run into the case where the manifold is a sphere. There are many situations where the sphere is the hard case. And the reason the sphere could be the more difficult case is that it has so many isometries. Okay, so here are some references on that. So the first one was Oscar Campoli, who looked at isometries of constant displacement on Stiefel manifolds. There are a few problems with this paper, but the idea was correct. And then the idea came out of to show the idea correct. What I had to do was So the Stiefel manifold, you have SO of, say, K plus L, not SOK. So the Stiefel manifold is fibered over a Grassmann manifold, and of course the fiber looks like a group manifold, SOL. So it's a typical situation where you have symmetric spaces, where you understand the isometry groups very well. And to abstract this situation, you have the base, you have the fiber, you have isometry, so you have constant displacement, and you look to see how it goes along the two. And the point is that if you're in a situation where you minimize this distance, then you're maximizing this distance, and then if you have enough flexibility, you can increase this distance without decreasing this one, and see that you can't have constant displacement, except for some particular cases. So using Kempler's idea, one can deal with a situation where you have some sort of vibration. So we can think of it in some cases as generalizing this as sort of a one can manage most of the positive curvature manifolds in this way, but there are a couple of spheres where this doesn't work. There are three cases where it doesn't work very well, and there one just has to do a lot of calculation. But again, for the positive curvature, strictly positive curvature, things depend very much on the idea of the Stiefel manifold fibered over the Grassmann manifold. Okay. Now let's step back for a moment and see we have a sort of a dichotomy. Let's ignore the Euclidean factors. I mean, then there are two cases, unbounded and bounded. In the unbounded case, this is the situation where the evidence is that isometries of bounded displacements are just ordinary translation along Euclidean factor, which we got rid of. So with no Euclidean factor, they have to be trivial or somehow come from some central element in a group manifold. So negative curvature we already saw. The argument works for manifolds without focal points. Homogeneous under a semi-simple group with no compact factor. That also works if you're careful. And then there's Riemannian manifolds homogeneous under exponential solvable group of isometries. So that's one aspect, the case where you have where bounded isometries are severely limited and the homogeneity conjecture is easy. Then there's the case where the where basically you're coming into compact manifolds, and there you have symmetric spaces, and you have like Stiefel manifolds over Grassmann manifolds with some technical conditions. And so, for example, this is the more general situation for those technical conditions. You have the isometry group, you have M is like a Stiefel manifold, fibroed over a Grassmann manifold. And each of them, say, with normal Riemannian metrics. And gamma is a finite subgroup of the centralizer of J times K2. And then it's acting this way. And this is isometric and transitive, and so the quotient is homogeneous. So what you have to do is assume constant displacement, get into this situation where you have the base and the fiber, and then use it to show that you're in this situation where you can trace through gamma. Okay. So that's somehow the general philosophy of what's going on. And now let me, let's see, how much time do I have? You have 20 minutes or? Okay. So let me indicate the idea is the proof. So sectional curvature, I already said a few words about connecting with this geodesic ribbons and filling out a flat, totally geodesic strip. And that would give zero curvature in those along that strip. So, and you get ordinary translation. So along with sectional curvature less or equal 0, as I said before, this homogeneity conjecture is correct. Every isometry, the quotient is homogeneous precisely when you're dividing out by a group of isometries of constant displacement. Now, if you have now I mentioned the same thing for some groups of some group manifolds which are, for example, solvable, and also semi-simple. Maybe I should just skip over these things. Well, if you have an exponential solvable group, for example, and a bounded isometry, then no, let me just skip this. Okay, so we're in the Riemannian symmetric situation now, and I want to somehow indicate how the argument works. So I have an isometry of constant displacement and a complete simply connected Riemannian symmetric space. And I break it up into a product along the de Rham decomposition, product of Euclidean space and some irreducible symmetric spaces. And then the isometry of constant displacement breaks up as a product. This takes a proof, but it's pretty straightforward. And each of these is constant displacement. So as I said, so now we're in the situation where we can assume that M is compact and irreducible. So the first case there is where M is a group manifold. So we have a compact simply connected group L, the group L, simple. And M is L cross L mod the diagonal. And the point is to show that gamma is conjugate in the isometry group to a group of left translations. Well, to do that, that goes in some steps. So first you will take an isometry of constant displacement, the element of the group gamma, and you write it as a pair, say G1, G2. Then it sends an element of M to G1, sends X to G1, XG inverse. And then you start looking for you look to see what it does to the group element G, where in there it's just a left translation by X, so the displacement is just the distance from the first factor to the identity. But then when you put on the other factor and apply it to something here, it's the distance for the second factor to the identity. And now you go in between and see you have some problem unless one of those two factors is central and can be moved over to the other. So if you're looking at something in the identity component, then it is indeed a left translation. It's conjugate to a left translation. Now, what about symmetry and then something in, say, S times G1, G2, that would send X to S of G1, X, G2 inverse, and then S would flip the two. And from that, you can find a fixed point. So it can't be constant displacement unless it's the identity. Then you have to start looking at inner automorphisms. And then inner automorphism situation you could reduce to the case where the element of gamma, where the element of gamma is a left and right translation. So you already know that's conjugate to something with left translation. Now you have to look at outer automorphisms. And there you just do a lot of matrix calculations, except for the E6. The E6 turns out to be easiest case, actually. So. There are some situations where the exceptional groups are easier to deal with than the classical groups. And the point is, here I'm really quoting from Nathan Jacobson, the point is that with the classical groups you have to see a pattern, and with the exceptional groups you can just compute without understanding what you're doing. Okay, so in this way you can run through the various possibilities for each element of gamma, and you always see that it has to end up inside the L naught cross L naught. And then if you have something non-trivial on both the left and the right-hand side, you know you have trouble unless you can move it over just to one side. So in that case, you end up, well, I'm being a little bit vague here, but I'm trying to sketch a long argument. And then you end up with gamma being conjugate to a subgroup of, say, the left translations. Now, now you can look at the case where M is G mod K, where G is simple. And there, you can first look at the case where the Euler characteristic is positive. And then running through the classification, through the Cartan classification of Riemannian symmetric spaces, you see that in most situations, the Euler characteristic is odd, has odd cardinality, and the group gamma would have to have the elements of order 2. So that doesn't work. So the group gamma would be reduced to having all elements of odd order. And you look at the automorphism group of G, and you see that's except for a few cases where you have triality, for example. The automorphism group of G, mod the inner automorphism group is odd order. So in that case, when G mod K has positive Euler characteristic, you can handle it using a bit of classification. And when G mod K is Euler characteristic 0, that is rank G bigger than rank K, you can, well, there aren't that many cases. You just treat them separately. Okay. Now I think I already described the idea when you have fibration of where the fiber is a space you understand and the base you understand. So that gives you the idea of the proof of the homogeneity conjecture for compact Riemannian symmetric spaces. Now, when you look at the proof, again, you see that the sphere is the hard case. So what's happening here is even though the sphere was done first, and that's the hardest case, then Riemannian symmetric spaces, there are a lot of them, and each one has to be dealt with, a lot have to be dealt with separately, but each of them is easier than the sphere. And then when you get to the other things, positive curvature and so on, each of those is easier than the Riemannian symmetric spaces. So somehow, as the isometry group gets smaller, the proof should get easier. But that's philosophy, that's not mathematics. So let me just quickly go back to the statement of the there should be an easier way to do this. Well, this was a mistake too. This is a mistake. Maybe I'll try to I'm not accustomed to this particular. Setup. So maybe at this point I'll just stop. And here's this, remind you of the statement of the homogeneity conjecture and the fact that it seems to be true and seems to be correct in many cases. So as I said at the beginning, it's the same, the conjecture is the same age as Toshi. And so that's why I felt that this would be an appropriate thing. And let me just say that happy birthday, Toshi, and I thank you for your attention to this talk.